Hello everyone! In this Python and control engineering tutorial, we will learn one very important scientific computing technique that can be used to implement classical and advanced control and estimation algorithms. Namely, we will learn how to automatically linearize nonlinear dynamical systems in Python. To perform linearization, we will be using Python's symbolic computation library called SymPy. The method presented in this video tutorial is very important for designing controllers and estimators for high-order nonlinear dynamical systems where it is practically impossible to perform linearization by hand. Before watching this video tutorial, it's a very good idea to get yourself familiar with the basics of linearization of nonlinear systems. For that purpose, I created a video tutorial and a web page that thoroughly explain how to linearize a nonlinear dynamical system. A link to this tutorial is given in the description below this video. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as more than 400 video tutorials that you can find on my YouTube page. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. Here's the outline of this video tutorial. To explain the linearization procedure, we will consider two test cases. Here's the first test case. It's a nonlinear pendulum with a state space model given over here. Then, after we explain how to linearize this system in Python, we will consider the second test case. The second test case is shown over here. It's an artificially constructed third-order state space model, and consequently we will explain how to linearize this system in Python. Here's our first test case. It's a nonlinear pendulum. The pendulum consists of the ball with a mass of m that's attached to the point Q by using the massless rod with a length of L. This ball, together with its rod, can rotate around the point Q. The angle of rotation is denoted by theta. G is the gravitational acceleration constant, and F is the control force. In our previous tutorial, whose link is given over here, we explained how to derive the state space model of the nonlinear pendulum. A link to this tutorial will be given in the description below this video. In the interest of the brevity of the current video, we will just briefly explain the derivation of the state space model. When deriving the state space model, the first task is to assign the state space variables. In our case, the state space variables are x1 is equal to theta, and x2 is equal to theta dot, that is, angular velocity. By using these state space variables and from the second Newton's law, we actually obtain the state space model given by the equation number 2. In this equation, the variable u is actually the external control input. That is, when deriving the state space model, we assume that the control force F is equal to the u squared. The state space model given by the equation number 2 can be written in the standard state space form given by the equation number 3. In this equation, bold x is the notation for the vector x consisting of the state space variables x1 and x2. F is a vector function and it's defined by two entries, f1 and f2, where the entry f1 is equal to x2 and the entry f2 is equal to this nonlinear expression. To linearize this state space model, we need to compute the Jacobian matrices of the nonlinear vector function f with respect to the state vector x and with respect to the control input u. The state Jacobian matrix is defined by this matrix. We simply take the first nonlinear entry of the vector f and we compute the partial derivatives with respect to x1 and with respect to x2. Then, The second row of the Jacobian matrix is composed of partial derivatives of f2 with respect to x1 and with respect to x2. And by computing these partial derivatives, we obtain this matrix. For example, the partial derivative of f1 with respect to x2 from this equation is obviously 1. In the same manner, we define the input Jacobian matrix. The input Jacobian matrix is actually a vector where the first entry is the partial derivative of f1 with respect to u, and the second entry is the partial derivative of f2 with respect to u. And here's the final expression. To linearize the model, we need to evaluate the Jacobian matrices at the selected linearization points that are usually denoted with the star superscript. We select the following state x star and input u star in linearization points. They are given over here. Then, by evaluating the corresponding Jacobian matrices at these points, we finally obtain our linearized A and our linearized B. And finally, the linearized model is given by this equation, where the new coordinate vector z represents the linearized state in the relative coordinates, and the scalar w is the relative input or linearized input. This state space model can be represented in the standard or in the compact form given by this equation, where A is the standard A matrix and B is the standard B matrix. In the sequel, we explain how to automatically linearize this system in Python. The first step, of course, is to import the necessary libraries. We will need the NumPy library, and to linearize the model, we will be using the SymPy library. Over here, I import the complete SymPy library. Next, we need to define all the symbolic variables. The first step is to define a symbolic equivalent of our state vector, and we do it over here. We specify the name x and we specify the dimension 2, 1. This means that we have 2 rows and a single column. The next step is to define the symbolic input u. We define it over here. And finally, we define the symbolic constants g, l, and m. We do it over here. The next step is to define the nonlinear state equation. We need to define this equation, and we do it row-wise. Here's the first row. x1 dot is actually equal to x2. However, since Python is indexing the variables from 0, x2 will correspond to x of 1 over here. Then, we need to define this nonlinear equation. We do it over here. I will modify this Python script by including a call to this function, initPrinting. This function is used to generate nice equations over here, as you will see it later on. So let's evaluate this script and let's see the output. Okay, let's look into our state function. Perfect. Looks amazing. And that's precisely our nonlinear state equation. Now, you can also look into the x. So here's x. And if you type something like this, x of 0, you will actually obtain x00, and that's precisely the variable over here. And if you type x of 1, you will obtain x10. Perfect. The next step is to perform linearization. First, we need to compute the state Jacobian matrix. The state Jacobian matrix is analytically given over here, and we can compute it in Python by simply writing our state function and by calling the method Jacobian. And we specify the symbolic variable that's used for computing the Jacobian. In our case, it's x. Similarly, we compute the input Jacobian matrix by calling our state.Jacobian, and we specify the variable u. And that's it. Let's see how this works in practice. And let's see the Jacobian state. looks amazing. That's precisely the expression, the analytic expression that we previously derived. And let's look into the Jacobian input. Here it is. Correct. Perfect. The next step is to select the linearization points. In our case, we are using 0, 0 for the state vector, and the input is equal to 1. To compute the A and B matrices, we need to actually evaluate our Jacobians at the state point and at the input point. To do that, we use the function subs. We simply write Jacobian state dot subs, then we specify the variable that we want to substitute, and we specify the expression, the numerical expression that we want to substitute for. Over here we are actually stating the following. In our Jacobian state symbolic matrix, we want to substitute the vector x with its components x0, 0 and x1, 0 with the numerical values that are given in this NumPy array. So let's do that. And here it is. We can see that actually we substituted x0, 0 with 0. That is, by analyzing this expression, cosine of 0 is 1, and that's precisely this expression over here, minus g over L multiplying 1, and that's it. We can do the same thing for the input. And the input is given over here. Here it is. Note again that the value of u is substituted, since over here u is equal to this expression, and over here we have 1, and that's it. Over here it should be observed that g, l, and m symbolic variables appear in these symbolic expressions. However, we can also substitute these symbolic variables by their corresponding numerical values. Over here I'm substituting g with 9.81 and l with 1. And let's see the resulting expression. Voila, here it is. You can see that all constants and symbolic variables are substituted by their numerical values. We can do the same thing for the B matrix. We do it over here. And here's our B matrix. Perfect. This was the first approach for linearizing the model. However, there is a more elegant and faster approach. And here's the second approach. The idea over here is to start with our Jacobian state that has a general form given over here, and to start from Jacobian input given over here, and to first substitute G, L, and M in these expressions. So let's do that. Consequently, we defined this Jacobian and this Jacobian. Next, let us create functions that will evaluate these Jacobians for given values of x and u. To do that, we use a very powerful function called lambdify. Lambdify is used like this. The first input argument of the lambdify is the symbolic variable. For example, let's look into our state Jacobian. It looks like this. We want to create a function that will take x values and that will compute the A matrix. That is, that will evaluate this Jacobian with respect to the given value of x. This means that in the lambdify function, the first argument will be x, that is the symbolic variable that we use as an input argument of our new function, and the second input argument of lambdify is the actual symbolic expression. So let's do that. And here's our A matrix function. Obviously, it's a Python function. Perfect. We do the same thing for our input Jacobian. we specify u as the variable, and we specify the symbolic expression. Here it is. And finally, we have actually two functions, A matrix function, B matrix function, that will create A and B matrices for the given values of linearization points. We simply specify the state linearization point and the input linearization point, and as the result, we will obtain the linearized matrices. Here's the A linearized matrix, and here's the B linearized matrix. A nice feature of this approach is that we directly obtained the NumPy matrices. Perfect. Next, here's our second test case. This is an artificially constructed third-order nonlinear system. Here's the state equation that can be compactly written in this vector form given over here, where the vector x is the vector of state variables, f is a nonlinear vector function, and where f1, f2, and f3 are defined over here. Again, let us first analytically compute the Jacobian matrices, such that we can test the Python implementation. Here is the state Jacobian matrix. We simply take f1 and we compute the partial derivative of f1 with respect to x1, x2, and x3 to obtain the first row. The second row is actually computed by computing the partial derivative of f2, and the third row is constructed by computing the partial derivatives of f3. And here's the resulting state Jacobian matrix. The input Jacobian matrix is defined by computing the partial derivatives of f1, f2, and f3 with respect to input u. And we obtain this input Jacobian matrix. Perfect. Let us select these linearization points. X is equal to this vector, u is equal to this value, and finally, if we substitute x star in our state Jacobian, we obtain this matrix, and if we substitute our u star in this expression for the input Jacobian, we obtain our B matrix. Let us perform this linearization in Python. Again, the first step is to import the necessary libraries. We import the NumPy library, we import the complete SymPy library, and we called init printing. Next, we need to define the symbolic state vector. Note over here that the state vector has 3 entries. Consequently, we need to define a matrix symbol with 3 rows and a single column. Then we define the symbolic input u. Next, we need to define the nonlinear state equation. Here is the definition. x2 is actually x1 in Python, x3 is x2 in Python, and here is the third nonlinear equation. It's defined over here. Next, we need to compute the Jacobians. First, we need to compute the state Jacobian. To do that, we call our state function dot Jacobian, and we specify the symbolic vector x. And in the same manner, we define the Jacobian input. We call the state function dot Jacobian u. Next, we select the linearization point. The linearization points are given over here. 1, 0, 1 for the state, and for the input it's 0. And finally, over here we create 2 functions. We use the lambdify function to create a function that will evaluate our Jacobian, that is our state Jacobian, for the given value of x, and we do the same thing for u. That is, we create a function that will evaluate the input Jacobian for the given variable u. Let's do that and let's see the expressions. First, let's evaluate this part. But before we do that, don't forget to raise the workspace, and let's clear our workspace. Here's our state function. Okay, perfect. Next, let's compute the Jacobians. This is the state Jacobian, and this is the input Jacobian. I made an error here, so I'll erase this and I will repeat everything. This is our input Jacobian. Perfect. Next, let's define the linearization points. Here they are. And let's create our functions. And finally, let us call these functions by specifying the state linearization point and by specifying the input linearization point. This is our A matrix. Here it is. And this is our B matrix. Here it is. Perfect. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.